Hello everyone, welcome back to my channel. You are learning with Dr. Shobha Nikam. In this video, I'll talk about construction of MOSFET, its working and characteristics. So MOSFET is an active device. It means it can control flow of electrons. Then there are two types of MOSFETs, depletion MOSFET and enhancement type of MOSFET. The basic difference between two is in depletion MOSFET channel is already present, whereas in enhancement type MOSFET channel is initially absent. Then again there are two more types of MOSFETs based on type of channel, P channel MOSFET and N channel MOSFET. So here today I'll talk about implementation of N channel enhancement type of MOSFET. For implementation of N-channel MOSFET, we need to take some base material. So for NMOS, base material is P-type substrate. So this is a P-type substrate. Sometimes we call it as body terminal also. Then here we will take metal contact, and this is a body terminal or substrate terminal. Then in case of N channel MOSFET, substrate is positive and we will create two N wells. This is our first N well and this is our second N well, and material is negative. One terminal is called as drain terminal and another terminal is called as source terminal. So, and again here we will use metal for contacts. So this is our drain terminal and this is our source terminal and metallic contact. Then we will have, then you need to understand, in this is P type of substrate, this is N type of substrate. So here it forms PN junction. So there is a depletion region around this PN junction. Depletion region. Then there is one more terminal which is gate terminal. In case of gate terminal is not directly connected to the body terminal. It is isolated, and for isolation we use silicon dioxide, or sometimes it is called as gate oxide. This layer is very thin layer. So here we'll have SiO2 layer. This is our SiO2, silicon dioxide layer, a thin oxide layer. Width of this SiO2 layer is generally 1000 angstrom units. Then again gate terminal is connected through metallic contact. So here is our metallic contact. This is our gate terminal, and that is why name is given is metal oxide semiconductor field effect transistor. Here you can see to flow current between drain and source terminal, channel is absent. So to create that channel we need to apply some voltage at gate terminal. So here in P substrate, majority charge carriers are holes and minority charge carriers are electrons, and then there are immobile ions also. So here to create negative channel, this is N channel MOSFET. To create negative channel we apply positive voltage to gate terminal. So we apply voltage between gate and source. This voltage is called as VGS. So because of this positive plate which is connected to gate terminal, it will attract negatively charged particles or electrons, or we can say because of uncovering of negative immobile ions, they'll get deposited here. These negative immobile ions will get deposited here. When we increase this VGS further, width of channel will get increased. So in this way channel gets created. So you need to remember, we need to apply voltage at gate terminal to create the channel. More value of VGS, more is the width of channel. And to create negative channel, VGS is always positive. In case of P channel MOSFET, channel is positive, so applied voltage is negative. Now here, let's understand working of N-channel MOSFET. Now channel is created by applying voltage between gate and source. You need to remember this VGS must be greater than that of threshold voltage. VGS must be greater than V threshold to create a channel. Now let's apply voltage between drain and source terminal. Positive voltage to drain, positive plate to drain, and negative to source. And this body terminal or substrate terminal is internally connected to source terminal. So here initially when no voltage is applied between drain and source, then current doesn't flow through MOSFET, and this is called as cutoff region. Cutoff is when current doesn't flow through MOSFET. Then some voltage is applied between gate and source, we'll call it as VGS1. So when some voltage is applied between gate and source, channel is created. Now when VDS increases, when voltage between drain and source increases, current through this channel also increases linearly. So current also increases linearly up to this point, which is the voltage at this point is VGS minus V threshold. At this point, voltage is similar to this voltage between drain and source is same as VGS minus V threshold. Then current increases linearly. Then what happens? You can see this is negative material which is connected to positive plate. And this substrate is positive but it is connected to negative plate. So this PN junction becomes reverse biased, and because of the reverse bias of PN junction, width of this depletion region continuously increases, and because of increased width of this depletion region, channel width at this point decreases. Channel width decreases, and this is called as pinch of region. Pinch of region. And because of this pinch of region and because of decreased channel width near drain terminal, and why it is happening? Because of reverse biased PN junction, the drain current cannot increase. So here drain current remains almost constant. This is for VGS1. When we increase VGS further, when we increase voltage between gate and source further, then what happens? Here, when VDS is less than VGS minus VTH, again current increases linearly up to this point, and then after this point it remains constant at VGS2. So here VGS2 is greater than that of VGS1. When we further increase voltage between gate and source, then again here current increases and then it remains constant. So this is VGS3. You need to remember VGS3 is greater than that of VGS2, which is greater than that of VGS1. And this region is called as linear region. This is linear region where current increases continuously, and this region when current is constant is called as saturation region. This is our saturation region. So here you can see, even if VDS increases, the drain current remains constant. So here current is independent of VDS. So now let's write the equations for ID, that is our output current. So in cutoff region, very first is cutoff region. Cutoff means here, this point, when no drain to source voltage is applied. So what happens in cutoff region? Current doesn't flow through it. So ID is equals to 0. And you need to remember why it is, because VGS is less than V threshold. When gate to source voltage is less than that of threshold voltage, it means channel is absent. Channel is absent means current cannot flow through MOSFET. Then next is in linear region. In linear region where current increases continuously. So ID is equals to mu mobility COX gate oxide W by L width and length of the channel into VGS minus V threshold minus VDS by 2 into VDS. So here the drain current depends on mobility of charge carriers, capacitance of oxide layer, W by L, width by length of channel, VGS minus V threshold minus VDS by 2 into VDS. That is for linear region. Now you need to remember, in case of saturation region, in saturation current is almost constant. So ID is equals to mu COX divided by 2 into W by L, and now it is completely dependent on voltage between gate and source only. Bracket square. Here the drain current is independent of VDS, voltage between drain and source. So MOSFET works in 3 regions: cutoff, linear and saturation. In linear region, current increases continuously. In case of saturation, current remains constant. To flow current, we must apply voltage between drain and source terminal, and to create channel, we must apply some voltage between gate and source terminal. This is pinch off region. It is created because of reverse bias of this PN junction. So, this is the working, the construction of MOSFET, working of MOSFET and characteristics of MOSFET. Thank you so much for watching.